All right. Good morning or afternoon, whatever hour I have you. So today we're going to do some guided notes because everyone's at a few different levels as far as where we're at in the pacing of this unit. So if we do guided notes, then you guys can come back and have access to these. So guided notes. Here is the general vocabulary of the notes. You can come back and write these down if you miss them, but you'll see them throughout the hour. Okay, so what we're talking about is groundwater. And groundwater lies beneath the ground surface, filling pores in sediments and sedimentary rocks and fractures in other rock types. Soil and rock act as giant sponges. They are full of tiny pores and cracks that are usually less than millimeters in size, which allow the water to infiltrate and collect underground. Okay, so there is water underneath most of us right now. Okay, so this represents about 0.6% of the hydrosphere, which the hydrosphere is the entire collection of Earth's water. It's actually 35 times more water in the groundwater than in all lakes and rivers combined. So 0.6% doesn't seem like a lot, but when you compare it to 35 times more than all the lakes and rivers combined, it's quite a bit. So it also it's resupplied, which means that it's refilled by slow infiltration precipitation. So slow, it's slow because that precipitation has to get down. To infiltrate means um, to break through that ground and get back into the groundwater reservoirs. So it's generally cleaner than surface water, and it's accessed by wells. Okay, so next couple things let's talk about is porosity. Porosity is the percentage of rock or sediments that consist of voids or openings. Okay, voids are just holes, like openings. It's the measurement of the rock's ability to hold water. That right there is key. Okay, so if you do not have a porosity rock or a rock that's porous, it can't hold water. All right, loose sand has about 30 to 50% porosity. Compacted sandstone may only have 10 to 20% porosity. Okay, sandstone is going to be squished together. There's not going to be holes. If you don't have holes, you can't hold water. Your body is made of holes. All your little sweat glands, and you hold a lot of water. Okay, permeability. It's the capacity of a rock to transmit fluid through pores and fractures. All right, interconnectedness of pore spaces. So not only do you have to have a porous rock, but you have to, if you want that water to flow or transmit fluids, then you have to have those pores connected. Okay, so most sandstones and conglomerates are porous and permeable, which means they have holes, and those holes are connected in some way, shape, or form. Therefore, you can have a fluid flow through it. Granites, schists, and unfractured limestones are what we call impermeable. Well, if permeability is the ability to transmit, im meaning the opposite, when you have something that has an im in front of it, it's think about imperfect. I can't think of another. But anyways, so impermeable means that it is not able to flow or transmit fluid. Okay, the water table. I'm sure you've all heard this, so you've probably learned it back in elementary school, but it is the subsurface zone in which all rock openings are filled with water, is the Peritic or saturated. We call it the saturated zone. So the top of the saturated zone is the water table. Okay, so if you go down far enough, but not too far, you're gonna reach this saturated zone. It's when the ground holds as much water as possible, which means all the openings are filled with water. Okay, so this is oftentimes water level at surface of most lakes and rivers. This corresponds to your local water table. Okay, so um, and around here it might be a little tricky because like De Smet is actually a reservoir, so I don't know if that counts. I don't know if the surface level of Lake De Smet corresponds with our local water table. Um, but I would bet up on the mountain at Sibley, because Sibley is more of a natural lake, that the surface of that lake also, if you were to cut through the ground going away from the lake, um, parallel to the top of the lake, you would be in the water table. Okay. Above the water table is an unsaturated region called the vadose zone. Okay, a perched water table is above the and separated from the main water table by an unsaturated zone. Okay, so commonly produced by thin lenses of impermeable rock, shales or clays with permeable ones. Okay, so a lot of times you'll have a impermeable layer and then you can get a perched water table. That perched water table is going to be made up of permeable rocks but surrounded by impermeable rocks, kind of like a little water bubble underground. Okay, so groundwater movement. The groundwater does move just like our water on the surface moves. Okay, the movement of groundwater through pores and fractures is relatively slow. Typically, it's centimeters or meters a day. Um, and that's relatively slow compared to water in surface streams. All right, flow velocities in cavernous limestone can and cavernous is like a holy cave, like you think of cave. So um, it's limestone with holes, can be much higher. That can go kilometers a day. Flow velocity depends on two things: slope of the water table. How steep is that water table? We know that steep things are going to flow more. And then the permeability of the rock. Because remember, permeability is the ability to move a liquid. Okay, we'll come back to Darcy's law equation, the V equals Ki, but jot that down anyways. Okay, aquifers and aquatards. Aquifers are a body of saturated rock or sediment through which water can move easily. Okay, so sandstone, conglomerate, well-jointed limestone. By well-jointed limestone, I mean limestone with like holes in it. Sand and gravel and highly fractured volcanic rock. An aquitard is a rock or sediment that retards groundwater flow due to low porosity and permeability. This is like shale, clay, unfractured crystalline rocks. Okay, so let's talk about an unconfined versus a confined aquifer. We just talked about what an aquifer was, but an unconfined aquifer has a water table and is only partly filled with water. Okay, it's going to rapidly recharge by precipitation infiltrating down to the saturated zone. Okay, so that's an unconfined. Now, a confined aquifer is completely filled with water under pressure, which we call a hydrostatic head, and it's separated from the surface by impermeable or a confining layer aquitard. Okay, remember we just learned what an aquitard is. So a confined aquifer usually is separated by a aquitard, which means there's very slow recharge. Okay, because if you want to look at the picture right there to the right, that's examples. Okay, you can see that you have those distinct layers, okay, different layers in those rocks, and you're going to have some impermeable aquitards, and it's not going to allow that water to recharge down into your aquifer. We're going to probably come back and read the more about aquifers, but wait for my command. Okay, wells. A lot of you, if you live out in the country, you have wells. City people, maybe you don't have wells. So what a well is a deep hole dug or drilled into the ground to obtain water from an aquifer. Okay, remember an aquifer, you can have water. Okay. For wells in unconfined aquifers, water level before pumping is the water table. Okay, so in unconfined aquifers, you have easy recharge from precipitation infiltrating. So the water level is at the water table. Remember that water table is where we store that underground water. So the water table can be lowered by pumping, and this is a process called drawdown. Okay. If we have time, I've got some cool readings and some YouTube videos about drawdown and the hazards it's having across the world. Okay, water may rise to a level above the top of a confined aquifer, and what this does is it produces an artesian well. And if you know anything about an artesian well, it is like a free-flowing well. They're kind of cool too, not super common. I'm trying to think if there's any. I bet you there's some up on the mountain. I will bet there's some up on the mountain. Okay, so springs. I'm not talking like birds and flowers, that kind of spring. We're talking water springs. So a spring is where water flows naturally from rock or sediment onto the ground surface. Oops, let's go back. So if you want to look, you can see that basically what a spring is you have water that naturally flows from the rock to the surface, and you can see it's in many different forms. Typically, it happens on a hillside. We have springs all over. Lots of springs up in the mountain. You probably maybe have springs if you live out in the country. A lot of ranchers, I believe, get their water from underground springs, and then you can build your waterways to water your animals. All right, so here's a little example of what artesian wells look like. There's non-flowing and then there's flowing artesian wells. So if you just take a look, you've got this drilled hole or canal or whatever it is. Sometimes it's natural, but what it is the water's being pushed up through it. It's kind of like a volcano if you think about it. So the water in the artesian well, or the water down here in the aquifer, is covered and surrounded by aquatards. Okay, those aquatards are going to create more pressure on the aquifer. That pressure is going to make the water rise to the surface naturally. Okay, so let's talk about balancing withdrawal and recharge. If groundwater is withdrawn more rapidly than it's recharged, the water table is going to drop. Okay, fair enough. So dropping water table can lead to ground subsidence. Okay, subsidence is when if you subside, you kind of pull away. So surface of the ground drops as the buoyancy from the groundwater is removed, allowing rock or sediments to compact and sink. This is how sometimes sinkholes are formed. Not all sinkholes, but a lot of times when you have the subsidence of the water table, okay, there's no longer that water creates a pressure and it pushes up on the ground. If that water's not there, there's no pressure pushing up, so it's going to fall down and create a sinkhole. Subsidence can crack foundations, roads, and pipelines. After areas of extremely high groundwater pumping, such as for crop irrigation in dry regions, some areas have subsided 7 to 9 meters. So if we take away that water table underneath the ground, there's nothing there to hold the top layer of the ground up, and it sinks down. All right, streams and groundwater. An effluent stream receives water from the saturated zone. Okay, what that means is the gaining stream surface is local water table. Okay, so look at the top right corner. That is what we call a gaining stream. Okay, and you can see that the water table is right up there with the river. Okay, the surface of that river is right there at the local water table. An influent stream, it's when the stream loses water to the saturated zone. Okay, so are you receiving water from the saturated zone, or are you losing water to the saturated zone? Okay, so stream beds lie above the water table. Maximum infiltration occurs through steam bed, producing permanent mound in the water table beneath the dry canal. Okay, so in a influent stream, that stream dries up a lot faster. It gets way smaller because the water table wants to be full. So the water table is going to actually take away the water. All right, so here's another example. We've got an influent stream up at the top, and you can see that as it rains, that stream can recharge, and then that stream actually goes through the unsaturated zone down into the saturated zone of the water table. Okay, groundwater flows down, obviously like all other water. And then you can see that this effluent stream is the top of the effluent stream is also level with the saturated zone or the water table. Okay, so groundwater contamination. Infiltrating water may bring contaminants down to the water table. So some of these contaminants could be pharmaceuticals, pesticides, herbicides, or herbicides, whatever you want to call it. Fertilizers, feedlots, mercury and gold mining, landfill pollutants, heavy metals, bacteria, viruses, and parasites from sewage, industrial chemicals, PCB, TCE, acid mine drainage, radioactive waste, oil, and gas. Okay, so as you might predict, landfills. Okay, so landfills, you get water going through those landfills. That water is taken down to the water table. Well, I don't know about you, but I don't want to drink water that's gone through piles and mounds of somebody else's garbage, or even my own. So sometimes that can be a pollutant. Also, if you have old gas storage tanks and they leak, okay, so that gas could leak down into the water table as well as toxic chemicals. Once our water table is contaminated, you cannot uncontaminate it. Okay, so think of how hard it is to help and fix any oil spills that we have in the water. Okay, so if we have big tankers that spill oil in the water, it's hard to clean up that water. All right, imagine that, but it being underground. It's extremely hard, next to impossible, to clean a aquifer if it has gotten contaminated. All right, so I want you to try this assignment. Pick your favorite groundwater contaminant, and I want you to just write a paragraph that describes the following. Okay, you guys can read through there. I say do the beginning of class next Monday. Just finish it today. So you'll be good. Finish it today if you're in class. It's kind of cool. So you'll have to do a little research and use Google, and it should be pretty simple, just a simple paragraph. So get that done along with making sure that you finished up these notes.